Now let's take a look at the regression assumptions. In previous module, we had mentioned that there are 4 basic assumptions for regression. Number 1, that the mean of the residuals is 0, that the residuals are normally distributed around the regression line, that the residuals have constant variance or homoscedasticity, and that the residuals are independent of each other. The next few slides will demonstrate how we checked for each of these. Now, there are more advanced methods, so we're going to consider these introductory level tests and general observational tests. In Excel, we want to make sure all of the appropriate boxes are checked off to give us all the plots and measures possible. So when we use the data analysis add-in in Excel, choosing regression, the following dialog box opens. And this image shows what you want checked off. At the bottom, it shows all of the residual plots and all of the normal probability plots. Now, the first test is actually very simple. Once Excel has run the regression, you're going to see a section for residual output, and it contains all of the information about the residuals. The column called Residuals, which is going to be the third column over, is the actual error for each observation. It doesn't contain the average itself, but simply using the average function, we can calculate what the average of the residuals are. And as you can see, we have a small number because we have negative 1.6 times 10 to the negative 15 power. And we can consider this very close to 0. It won't be 0, but it should be very close to 0. So if you had a number like 3 or a number like 5, there's a good chance that your residuals are not close to 0. Now, the regression assumption 2 is that the residuals are normally distributed. While other statistical applications will provide more robust tests for normality, Excel does not. But that's okay. It does provide a normal probability plot. In general, we wish to see an upward sloping set of points, kind of an S-curve. A majority of the points in the middle should follow a 45-degree line or thereabouts, and if the two tails curve away from the line, that's considered fine. We would expect to see that. If there are a large number of data observations, you don't have to worry too much about this if you're not sure. If it looks something like on the left, you'll be fine. Some statistical applications will provide a test for constant variance. If you plot the residuals on a chart, you can see that they appear to rise above and drop below the horizontal line at 0. So that horizontal line at 0 is basically our line that says the residuals are 0. Everything above the line is our positive residuals, everything below the line is negative residuals. And if we have constant residuals, it will appear as though the plots will go above and below the line in a constant manner. Had there been a pattern, you might see the residuals curving upward or downward, or even fan from small to wide. The blue line on the chart indicates what a curved pattern might look like. These residuals do not follow that pattern. The fourth regression assumption is that the residuals are independent, and this is very easy to spot graphically. As you can see on the chart on the right, there's an obvious pattern to the residuals. As the residuals go up, generally the next one goes up. We call this a dependence between every residual, and we call this autocorrelation. Autocorrelation of residuals can cause many problems for regression, and there are some techniques that will help alleviate this problem. Autocorrelation is usually indicative of a time series problem, and time series problems are usually data points that are date or time driven, where each successive data point is related to previous data. So stock prices are an example of this. We can calculate an autocorrelation value fairly simply using Excel. And Excel doesn't really provide that for you, although some of the add-ins tools will do this for you automatically. But it's a fairly simple statistic. The formula has 2 basic parts. We basically take each residual and subtract the residual before it. We square it and we add all those up. And we divide that by every error that we have squared, and we add those up. So the numerator subtracts each residual from the previous residual and squares it, then sums up all of the values. The denominator squares each residual and sums it up. And the ratio will yield what we call the Durbin-Watson statistic. And the interpretation is fairly easy. A number greater than 2 is positively correlated, and a number less than 2 is negatively correlated. Numbers close to 2 indicate no autocorrelation. Now, what if you have numbers like 1.9 and 2.1? Well, we consider those close to 2. So while we can set up a hypothesis test for autocorrelation, we can state for the purposes of this module, if the Durbin-Watson statistic is below 1.5 or greater than 2.5, then we have autocorrelation. And we'll need to use time series techniques to solve the issues with autocorrelation. Now, what happens if the assumptions are violated? In those cases, the analyst must make an assessment as to whether the violations are severe enough to warrant any changes. Therefore, just because you have a small violation in the assumption doesn't mean that you're not going to use what you've calculated. It means that the analyst has to take a very close look at what is happening to determine whether or not that violation of the assumption is important or not. If there is a violation, the analyst may decide they want to transform the y variable in order to fix the violation. And there are different things that can be done with regards to transformations, which we'll see in another module. The analyst may need to consider a different method based on the information available. So that means they may need to choose a different type of regression or even a time series, as we had just mentioned. We need to determine if single outliers or multiple outliers are the cause for the violation assumptions. It is possible that one or two key outliers are causing us to violate the assumptions entirely. If so, then we need to determine what we're going to do with those outliers. Do we allow the violation of the assumptions? Do we remove the outliers? Or do we do something else? And finally, we can consider changing or reducing or increasing the data set to see if the results change. Now, violation of the assumptions don't always mean that the model doesn't have value. The analyst has to make an assessment based on the information available and the effectiveness of the model in doing its predictions. So there are a number of different ways that the analyst can handle violations of assumptions and a number of techniques at a more advanced level to resolve any issues from it.